All right, class. In this question here, we have experiment 1 and experiment 2, where we have a ball that is, in experiment 1, it's released from rest. In experiment 2, it's horizontally rolling off the table. And so we have this position versus time graph here given in experiment 1, experiment 2, and the vertical position versus time. So we have a horizontal and a vertical. And so I always like to tell us to think about either slope or area. So I know with position and time, I know the slope is my velocity. And I know the area, that really doesn't tell me anything here, but we know that the slope tells us about the velocity in either one of these graphs. So as we look to this first question that we're being asked here, which ball reaches the ground first and at what time? And so by having this type of question, I set up my variables, my y, y naught, v, v naught, a, and t. I could have done it in terms of x, using x and x naught, and this v in the y could be this v in the x. I'm talking about the y direction here because if it reaches the ground first, that means it has the final position being at that point 0. So it has to hit the ground at y equal to 0 meters for both experiment 1 and experiment 2. And we see that both of them start at 1.5 meters above the ground in the vertical direction, and in the horizontal they start at 0 as well. And then when they end, we don't know where exactly or when they'll hit. We don't know in terms of the time, so we can't really say. It looks like it's going to be around 0.5 right in here, before 0.6, so after 0.5, before 0.6, somewhere in that time. But we don't know exactly the time graphically, but we can use our equations to set this up. I know then the y naught is that 1.5 for each meters. The v, we don't know their vertical velocity, but we do know their initial velocity. In experiment 1, it's released from rest. So that means 0 meters per second starting from rest. And in experiment 2, it's going horizontally. So the initial velocity in the y direction is also 0 meters per second. They both have the same acceleration. That's that negative g. And then the time, well, this is what we're trying to find. Well, we all have the same inputs here, so the same parts. So we can already tell that the ball that reaches the ground first is going to be both. So both experiment 1 and experiment 2 are going to hit at the same time. So now we just have to calculate. And how we're going to do that is we have to decide based on our equation sheet which one of these equations works best. We know the starting position, final position, so we know starting position, final position. We know the initial velocity. We know the acceleration, and so therefore we can get the time. So it looks like if we use this equation right in here, then we can use that. Now I subbed out the x for the y because I'm dealing in the vertical component. So the equation I'll use will be my y equal to 1/2 a t squared plus v naught times t plus y naught. And we're going to try to solve for t, where the initial velocity is 0. So that term goes to 0. And the initial position we know the acceleration we know, and this we know. So I'm going to move this over here, making it a y minus a y naught. That's going to equal to 1/2 a t squared. Now this y minus y naught, this is also the vertical displacement. So it's that change in y is going to equal to this 1/2 a t squared. And we can leave it as this y minus y naught. I just like also writing this in because, well, I like it. And it's equal to this 1/2 a t squared. So if we solve for the t, divide by the 1/2, which is multiplying by 2, divide by the acceleration, and then we can square root. So now in terms of our variables, acceleration is gone, the 1/2 is gone, the square root gets rid of the squared. So now our t is square root 2 times the y minus y naught, which would be 0 minus a 1.5, divided by a, which is negative g, so negative 10 meters per second squared. And then we type it in to our calculator and we get about 0.547 seconds. So now we know the time that it takes to fall. The second question that we're being asked is how far horizontally does the second ball there travel in experiment 2? So this is where, once again, we can set up our variables because we're talking horizontally. Now we have x, x naught, v, v naught, a, and t. So when we're dealing in the horizontal direction, we know the acceleration is 0 meters per second squared, and we can see graphically that it shows that this position versus time, this is a linear relationship, therefore there is no acceleration. We also see that the v naught, whatever value this is, our final velocity will equal to our initial velocity. Once again, that's because our acceleration is 0. Our time, we know it's going to be 0.547 seconds. We got this from the previous one. And we know the x and x naught by looking at some graphs. So if we try to figure out how far horizontally, this is what we're trying to get. The x naught is 0 meters. So since we have this, we can use that equation on our equation sheet by setting up, I'm trying to get what x is, that's a how far. The how far, x, we know x naught. V naught is going to be the same value as the value v. Acceleration is 0. So v naught times t plus this x naught will equal to our x. So the equation we have, x equal to 1/2 a t squared plus v naught times t plus x naught will give us our x is going to equal to this 1/2 of a t squared. So since the acceleration is 0, this is a 0 component. This is going to equal to our v naught times t plus the x naught. Just like in the car lab, we have this constant velocity times time plus the initial position. The initial position is also 0, so this x is just going to equal to this v naught times t. So the only thing we don't have here is what this v naught is. So we can get that because we do know that on here the slope is our velocity. Slope of our position versus time is the velocity. So if we go out 0.8 meters in 0.4 seconds, and our 0 point. So our V naught is going to equal to our slope. Our slope's going to equal to our V naught, which is change in position, change in time, which would be this 0.8 minus 0 meters on 0.4 minus 0 seconds. That's the slope, giving me a 2 meters per second. So then our x is 2 meters per second multiplied by that 0.547 seconds. So our x is a 1.094 meters. If I put this down to the sig figs of probably close enough, but I would just go with 1.1 meters. But let's say, for example, that we're given this as a multiple choice question, and it asks us here, which of the following conclusions can the student draw from these graphs? Well, we know a lot of stuff about this. The horizontally rolled ball travels a greater horizontal distance and takes a longer amount of time. So that has the time component had nothing to do with reaching the ground. The only thing that had to do with reaching the ground was in the vertical direction. And if you release the ball at a slower speed, it takes a longer amount of time. Well, that's not true. The ball that was released from rest reached the ground at the same time as the first one. Since both balls have 0 horizontal acceleration, they reach the ground at the same time. You only hit the ground when you hit the ground on the vertical direction, so it has nothing to do with the horizontal acceleration. But since they have the same vertical position, at a given time, they reach the ground at the same time. And then let's take a look at this next part where it says that in this experiment, we want to know the speed that it makes when it contacts with the ground. So in this experiment, we do know some information. We know the time it hits, and we know how far horizontally experiment 2 goes. But in experiment 1, we know the time it hits. But let's say, for example, we don't know the time. We can still work through this by writing out those variables, that y naught, v naught, a, and t. And that can help us get to the things that we need and what we're trying to get. What we're trying to get is the speed. This is what we're trying to get, this final velocity. We know the initial velocity in experiment 1. If it's reached from rest, it has a 0 meters per second. And it has a y naught, that was that initial height of 1.5 meters. And we know when it hits the ground, it's going to have a height of 0 meters. We also know the acceleration. The acceleration here is a negative g. The time in this, it wasn't given. We were able to calculate it, but let's say, for example, we're not given the time and we haven't calculated it yet. Well, we can still figure out the speed. If we look at our equation sheet, we have these 3 equations. Now in this third one, we have the final velocity. That's what we're trying to get here. And this initial velocity we know is 0. The acceleration we know is negative g. And we have this final position minus the initial position. We have final minus the initial. Therefore, we can use this third one. Because we don't know the time, we can use that third one. And if we set up our v squared equal to the v naught squared plus 2a delta y. Then from this equation, that goes to 0. Our v squared is equal to 2 times a negative g times our initial height minus, or rather our final height, 0. So 0 meters minus 1.5 meters, 1.5 meters. And square root, to get rid of that square. So now we have v square root of 2g delta y, which is, if we take 2 times 10 and times that by minus 0.5 minus there, cancels out, then we get this 5.4 meters per second. Now we could also have done from before, we know that v equals to a times t plus v naught. And if we knew the time, and we did in the previous problem of 0.547 seconds, we could have taken that, multiplied that by that negative g, and that would have also given us that velocity of 5.4. Now as we take a look to this next one, we have two students that want to determine the speed at which a ball is released when thrown vertically upward into the air. One student throws the ball into the air while the other student measures the total time in the air. The students use a meter stick to measure the release height of the ball. Which of the following equations should the students use to determine the speed at which it was released? So in this problem here, what we're figuring out is we're trying to determine the speed of balls released. So what I am reading here is that we're getting a dude to throw this ball going up, coming back down. And what we're able to measure is his release height and the time that they can measure. So that's what I'm getting in here. So they have a meter stick to measure this height h, and they can measure time. So what we're being asked here is which one of these equations could we use? And what we're trying to get is the speed that the ball started with. The speed that this was released. So we're trying to get that v naught. So as we read at this, we have use this equation from the moment of time when the ball is released to the moment of time in which the ball is at the highest point. If we were to do that one, if we measure the time from here to here, then that's not really going to tell us a whole lot, because we would know the y, we would know the y naught, the v is what we're trying to get, the v naught is what we would want to have, the a and the t. We would be able to measure this value, and this value. We don't have the v naught, and in this acceleration we would have that as well. That would also be g. But we wouldn't know the final velocity. We would know the starting, but we couldn't get the y. We couldn't get the height. So in part A, we couldn't get here. We could, and we could. We could measure that. So in question B, if we have this equation, the moment the time is ball released to the moment the time the ball hits the ground. Now this, in part B, we would be able to get the final height. We can get the final height where the ball hits. We can get the starting height where it's released, we're trying to get this initial velocity. We don't know the final velocity. We'll have acceleration and we'll have time. So from all this, if we know this initial stuff, then we could use that equation of y equal to 1/2 a t squared plus v naught t plus y naught. If we know the y, the a, the v naught, the t, and the y naught, 1, 2, 3, 4, and then we can get the one unknown. If we know the t, we know the acceleration, know the starting and the final position, then we could get this unknown. So then it would be us using this as solution B. In this next part, we have an object that undergoes acceleration as it travels along the straight horizontal section of track. Which of the following graphs could represent motion of this object? So once again, in this question, we're having an object that undergoes acceleration. So it has acceleration in a straight horizontal section of track. So there has to be acceleration here. So which of the graphs represent the motion? So as we look at this, we want something with acceleration. So I know in this graph, the slope is the acceleration. The slope of speed over time, that is acceleration. In this graph, this is a constant slope. So this is going to give us a constant velocity, because I know in a position versus time, that has a constant slope in this, so it has a constant velocity. In this position versus time squared, I know x equals to 1/2 a t squared, and when we did our acceleration lab, it was position and time squared that made this linear relationship. So this definitely shows an acceleration. And then a constant velocity. Constant velocity, then this has no acceleration. Constant velocity, making selection A and selection C viable. So on this next one, we have this dart that's going to be launched up. It's going to be launched up at this target, and the target, as soon as the dart is launched, the target has this string cut. So it says up here, the student wants to launch a toy dart toward the target that hangs from a light string. At t equals 0, the dart is launched. So at t equals 0, dart goes with an initial speed v naught at an angle theta naught above the horizontal of the ground. At the instant the dart is launched, the string is cut. So the dart is launched, the string is cut. The target begins to fall straight down. Positive horizontal direction is considered to be to the right, and the positive vertical direction is considered to be up. So they tell us the direction, and they tell us what's occurring. Now we're given a velocity versus time graph. And with this velocity versus time graph, we can understand a little bit about what's happening. We see this dart that starts with a positive velocity, and it reaches to a 0 velocity. So that tells me what the dart did was it launched up to its point. And then we see that this target, the target started with a 0 velocity and started to fall. So the target started here and started to fall. And they hit at the same time. And that's what this part says. So the student makes the measurements here, saying that at t equals 0, the target moves this vertical distance h above the dart, and the curve shows, all right, basically going from here to here is this height h. And this is the ground. We have the dart going up at this total height h. That's how far they move, and the dart goes up and reaches the zero velocity at the time it hits. So if it didn't hit the target, it would come back down and fall like that. And it would take the same amount of time to fall down as it did to go up. What we're being asked to do is figure out this height h. And so from this, if we just were to use this target area, that would tell us that's not going to tell us anything necessarily about the dart and the height. But what we're given here is if we find the area under the curve, if we find the area under the curve for the dart, then we'll get this height. We'll get up how high it is. So we do need to get the area somehow. But that is half the height. That's going to be half the height because it's only going to go from here to here, h on 2 and h on 2. Because if it takes the same amount of time for it to reach here as it would to go to fall back down, because it had a zero velocity at its highest point, then same amount of time up, same amount of time down, that means it's going to fall the same height going down as it went up. So going up, having half the height h on 2, and then it'd be another h on 2 for it to go all the way up. So that's why finding twice the area under the curve for that dart is going to be the one that you want to use. So you find that area and get it twice. Then the next question it asks, which of the following graphs could represent the vertical component of the velocity? So once again, we're looking for a vertical component. We want the velocity as a function of time. So in this vertical component of the velocity, on these graphs, we have to think about these as a v versus t. So I'm putting v versus t on all the graphs. Sometimes that helps make us understand what's happening. And we know that the dart had to start with a positive velocity. So if we have this starting at a positive velocity, then it's going to have a negative slope because it has this negative acceleration due to gravity. So we know that it should have a negative g for a slope. And it starts at a positive value. And for the target, it starts from rest. And it still has a slope of negative g as well. So that's where I would say option D. The rest don't work because the dart doesn't start with a zero velocity. So that's why I wouldn't say this one. Once again, the V naught for the dart is not zero. So that's why I'm not going to say this one. And here we have an initial velocity, but the V naught is zero for the target. That's why not this one. So last one here, on this last one, we have this student that wants to study the motion of an object that has constant acceleration. So we have to look for the following situations that have constant acceleration. When we use Earth's gravity, that is a constant acceleration. A toy car that it goes from rest, it travels at different loops. This different loops will give different accelerations. So that's why selection B is not going to work. Same thing here, we're going to have different accelerations from a water-propelled rocket. So that's why option C is not going to work. And if we release a car from rest and it travels down a ramp, So going down the ramp, it's going to accelerate due to gravity, so that's why option D is going to work. Because acceleration is going to be equal to a G. It's going to be proportional to G. It's going to be, I think, a G sine theta. So now that we have this, thank you.